Hello my friends and welcome back to the You Can Do TV channel. The steam turbine manufacturing industry is critical for energy production, as steam turbines are widely used for electricity generation in thermal, nuclear, and combined cycle power plants. As of recent estimates, the global steam turbine market size was valued at around $15.5 billion, with projections indicating a steady growth rate of approximately 3.3% annually from 2023 to 2030. This growth is primarily driven by the need for renewable energy and efficiency improvements in existing thermal power plants. Steam turbine manufacturing involves complex processes, from material selection and precision machining to assembly and testing. Typically, turbine blades and rotors are crafted from high-grade alloy steel or stainless steel, engineered to withstand extreme pressures and temperatures, often exceeding 565 degrees Celsius, 1050 degree F, and 24 megapascals, around 3,500 psi in large power stations. Each turbine blade is shaped with high precision, requiring tolerances within microns, 1/1000th of a millimeter, to achieve the required aerodynamic efficiency and durability. Manufacturing plants for large steam turbines require extensive facilities with specialized equipment such as large-capacity CNC milling machines, lathes, and vertical turning machines, which can accommodate the substantial size and weight of turbine components. A single large-scale turbine, typically used in a 1,000 megawatt nuclear power plant, can weigh over 500 tons, with rotors themselves weighing around 200 tons. The manufacturing process includes casting, forging, heat treatment, and precision machining, followed by assembly and stringent quality tests. Some advanced factories employ automation and robotic systems to enhance precision, reduce human error, and speed up production. The testing phase for turbines is particularly critical. Manufacturers simulate operating conditions to check the balance, vibration, and heat resistance of the turbines. Advanced sensors and testing equipment can monitor performance parameters, ensuring that each turbine meets strict industry standards before deployment. A fully assembled steam turbine undergoes rigorous testing over several weeks, ensuring reliability and efficiency in operation. Turbine blade machining is essential in power generation, where the process requires precise roughing, semi-finishing, and finishing to achieve the desired blade form and aerodynamic properties. Starting with medium-sized blades often made from martensitic stainless steel, duplex, or titanium, roughing focuses on shaping the blade rhombus and airfoil. This stage removes the bulk of material from the blank to establish the blade's foundational shape, using primarily round insert milling cutters and ball nose end mills. These tools excel in generating secure profiles with robust cutting edges, essential for maintaining part clearance and stability during machining. For rhombus roughing, the cutter should engage around 60 to 80% of the material, requiring a well-matched cutter diameter and tool path. Achieving optimal results necessitates a careful balance between feed rate, depth of cut, insert size, geometry, grade, and cutting forces. When transitioning to blade root machining, where the head and foot meet the blade's airfoil, different tools are required. A dedicated solution, often an indexable conical ball nose end mill, ensures precision in handling corners and shoulders. Semi-finishing and finishing processes for the airfoil demand high-quality tools to achieve fine surface finishes and precise geometries. Tools like the Mill 600 offer advanced features, such as an optimized cutter body and the patented eye-lock system, ideal for both rhombus and airfoil machining. For the shroud and hub, which involve complex transitions, the Mill Plura series ensures a streamlined finish. Finally, the head and foot areas benefit from face milling using Mill 490, which provides superior finishes with minimal vibrations. When machining the mounting slot, high-feed cutters like Mill 316 efficiently open slots, and Mill Plura completes finishing with varied depths. This end-to-end setup delivers precision and efficiency across each critical machining stage, ensuring turbine blades meet stringent performance and durability standards in power generation. The Advanced Turbine Efficiency Upgrade for F-Class gas turbines is a cutting-edge enhancement that significantly improves turbine efficiency and reduces emissions. This upgrade redefines the design of turbine components, especially the turbine blades, using the latest aerodynamic principles and advanced manufacturing techniques, like 3D printed vanes, with redesigned stator and rotor blades. The upgrade incorporates extensive instrumentation, including temperature and pressure sensors, to monitor and validate performance. The goal of this project, also known as the Advanced Urban Efficiency Package, is to modernize existing F-class turbine fleets, thereby supporting customer goals of efficiency and deep decarbonization, ultimately aiming for compatibility with up to 100% hydrogen fuel. The MGT 6200 and MGT 6100 gas turbines from MAN Diesel and Turbo illustrate advanced industrial gas turbine technology, providing efficient power for mechanical and electrical applications. The MGT 6200 is a twin-shaft model with a 6.9 megawatts output, ideal for driving compressors and other machinery. This turbine features two sections: the gas generator with a high-pressure turbine and an 11-stage axial compressor, and a separate power turbine operating at variable speeds. An electric motor initially drives the high-pressure shaft, which compresses intake air up to 15 bars before it enters 6 combustion chambers, pre-mixed with fuel gas. Inside these chambers, the compressed air-fuel mixture ignites, producing hot exhaust gases that expand, driving both the high and low-pressure turbines. The turbine's spinning blades propel compressed air through the turbine, creating high-pressure airflow for efficient combustion. The exhaust gases, exiting at around 460 degrees Celsius, can further generate steam for additional applications. The MGT 6100, in contrast, is a single-shaft turbine designed for continuous speed applications, such as driving generators. Sharing many modular parts with the MGT 6200, the MGT 6100 operates at a constant speed, which is ideal for generating power. This design saves 27% of components compared to the twin-shaft model, enhancing reliability and reducing emissions. The production process for turbine blades starts in the design office, where engineers model the blade using CAD software, adhering to stringent specifications that balance thermal, aerodynamic, and mechanical requirements. Every detail of the turbine blade, such as blade geometry, material composition, and surface finish, is carefully defined to optimize performance and durability. Once the virtual model is completed, it is sent to the Tools and Methods office to begin the industrial adaptation process. In this office, the engineers collaborate with the process and product development teams to define the most effective production strategy. A significant step here involves designing the cluster structure, a configuration that enables multiple blades to be cast simultaneously, optimizing productivity. Injection molds are created, albeit through outsourced manufacturing, to the exact specifications needed to create turbine blades with highly complex shapes and features. The production of turbine blades involves lost wax casting, an ancient technique modified with modern advancements to achieve precise, complex shapes. First, engineers produce a core, essentially a mold within a mold, which defines the internal cooling channels of the blade. A mixture of binder and ceramic material is injected into a core machine to produce this core. The cores are fragile initially, so they are baked in a special sand mixture to harden, allowing them to withstand high temperatures during subsequent stages. Each core is meticulously checked for defects and deburred before it is placed inside an injection mold. 4 cores in the case of this LEAP engine turbine blade are positioned in the mold to form the blade's complex cavities. Once aligned, molten wax is injected to form a replica of the turbine blade around these cores. This wax model undergoes ultrasound and radiographic testing to ensure the core is accurately centered and has not developed cracks during injection. The wax replicas are grouped into clusters, then cleaned meticulously to remove any contaminants. Cleanliness is critical to ensure adherence of the ceramic coating applied in the next steps. The clusters are then immersed in a ceramic slip, a liquid paste that creates a ceramic layer over the wax. A ceramic shell is gradually built up by alternating dips in ceramic slip and ceramic sand application. This process is repeated until a sufficiently thick shell is formed. Once the shell is complete, the wax inside is carefully removed through a process called dewaxing. This step takes place in an autoclave, where heat and pressure are applied to melt the wax out without cracking the delicate ceramic shell. Finally, the shell is baked to harden, preparing it for metal casting. Before casting, each shell undergoes additional inspections to check for impermeability. Any defect would compromise the casting process, so shells are inspected using methods like dye-penetrant testing with methyl blue solution, which reveals flaws by turning blue in defective areas. When the shells are deemed flawless, they are preheated and molten metal is poured into them. The cooling stage that follows is crucial, as controlled cooling enables directed solidification, creating a microstructure that enhances the blade's thermomechanical properties. Cooling rings are often used to guide this process, ensuring the material meets specific strength and resilience requirements. During cooling, the ceramic shell typically cracks due to metal contraction. This allows for easier removal in the shake-off stage, where mechanical vibrations help clear away the remaining ceramic. Finally, the turbine blades emerge as rough parts, grouped in clusters. These are then separated into individual blades for further processing. After shake-off, the ceramic cores used to form the blade's internal channels are still inside. They are removed by soaking the blades in a soda bath, which dissolves the ceramic material without damaging the metal. Once cleaned, the blades move on to various finishing stages to achieve the final shape and precision. One of the key finishing operations is rectification, where grinding refines the part's dimensions and smooths rough edges. For turbine blades that experience friction during operation, a metal alloy called stellite is applied to areas prone to wear. Precision 3D measuring machines then conduct up to 150 measurements per blade to ensure conformity with design specifications. In addition to dimensional accuracy, the blade requires cooling holes to enhance its performance at high temperatures. These holes are created using micro-drilling, a process that employs an electrode hollowed to allow water to pass through it. This electro-discharge machining technique, rather than mechanical drilling, enables the precise and minute holes needed for efficient cooling airflow within the turbine. After micro-drilling, additional components are soldered onto the turbine blade in preparation for assembly. Additional components are soldered onto the turbine blade in preparation for assembly. The soldered parts are heated in a furnace to ensure a strong bond, and the entire blade is heat-treated to achieve desired properties. The final steps include applying a thermochemical coating that further enhances durability. Each turbine blade undergoes rigorous testing before it is deemed ready for assembly. Tests such as macro control for grain structure, die penetrant testing for surface defects, ultrasonic thickness measurement, and digital radiography are performed to ensure structural integrity. An airflow test verifies that the cooling holes are functional and unblocked. For traceability, the blade is marked with a unique identifier via laser, weighed and photographed in its packaging to record its position in the assembly. With the quality assurance process complete, the finished turbine blades are ready for assembly. The production of spinner discs at here relies on precision investment casting. This process begins with creating delicate wax patterns, carefully handled to avoid damage. These patterns are coated with an investment material that forms a ceramic shell through repeated cycles of coating, sanding, and drying. Once the ceramic mold is robust enough, it undergoes high temperatures, preparing it to withstand molten metal. When the nickel or cobalt-based alloy reaches the required heat, it is poured into the mold, filling every intricate detail. After cooling, the ceramic shell is broken away and the casting is freed. The spinner disc then undergoes thorough cleaning, often using stainless steel shot blasting, ensuring it meets high-quality standards for use in glass wool production. PCC Airfoils in Mentor, Ohio, specializes in producing high-performance airfoils, such as blades and vanes, used in the hottest sections of land-based industrial gas turbines that power homes worldwide. This facility, located near Cleveland, employs cutting-edge technology and skilled professionals to craft durable products made from superalloys, primarily nickel and cobalt. These materials are engineered to endure extreme heat and lengthy operational durations. The process begins in the wax room, where wax pellets are transformed into patterns that are then assembled into molds. These molds undergo a ceramic coating process in the dip department, where robotic systems apply a ceramic slurry, creating a hardened shell. After the wax is removed from these shells, the ceramic molds are transferred to the foundry, where superalloys are poured to create the castings. Following casting, the parts move to the snag department for cleaning, grinding, and finishing, as well as various inspection stages like fluid penetrant, X-ray, and CMM checks to ensure quality. Finally, the finished airfoils are shipped to customers such as GE and Siemens. PCC Airfoils products contribute significantly to global power generation, with the Mentor facility alone helping supply approximately 1/3 of the world's electricity. The center focus on a streamlined, assembly line style process for turbine repair, ensuring efficient and rapid turnaround times that minimize costly downtimes. Upon receiving machinery, the process at the service center begins with a detailed inspection. For complete machines or individual parts, components are disassembled and thoroughly cleaned. The cleaning stage is crucial, as these machines often arrive with significant dirt buildup due to long operational periods. Following sandblasting, components undergo crack testing in a dedicated diagnostic section. The center uses a non-destructive testing method to identify any material fractures that might affect performance. Each part is then subject to a dimensional inspection, and findings are meticulously recorded by the repair management team, who provides a report to the customer. The center conducts many diagnostics, such as endoscopic examinations, directly at customer sites. This flexibility is supported by an extensive network of on-site technicians and field analysts, who perform preliminary inspections and maintenance on site. These field service fitters are equipped to dismantle, inspect, overhaul, and reassemble turbines and other key components, including generators, gearboxes, and auxiliary units, often ensuring that plant operations can resume with minimal delays. The workshop at Mulheim serves as a hub for more intensive repairs that are challenging to carry out on site. The facility is designed to handle crack tests, material tests, and other procedures to evaluate whether parts can be reinstalled or require repairs. If repairs are necessary, a detailed repair order is created, and components proceed through a series of steps, including machining and welding. Siemens Energy's technicians are trained in a range of processes, from precise machining to specialized welding, to repair existing parts instead of manufacturing new ones. This dual capacity, both for repair and new part production, ensures high adaptability and cost savings for clients. The service center employs advanced equipment capable of handling turbine parts and generators weighing up to 35 tons. In cases where even larger machinery is required, parts are transported to adjacent halls with more robust equipment. This flexibility is a significant advantage, especially when handling urgent maintenance requests. Siemens Energy has structured its operations to enable rapid responses to unexpected downtimes, recognizing the critical cost implications for customers when equipment is offline. This responsive capability is reinforced by Siemens' extensive network, allowing teams to call in support from other locations as needed. A highlight of the center's service offerings is its vacuum balancing system, a unique feature for achieving final rotor quality. This system balances repaired rotors at operating speeds, verifying that parts will run with minimal vibrations once reinstalled. Clients are invited to participate at key points in the repair process, particularly during initial damage assessment and the final acceptance stages. The Howden facility in Frankenthal, Germany, specializes in steam turbines and compressors, focusing on advanced coating and machining technology for industrial compressors and steam turbines. Using high-velocity oxygen fuel, HVOF coating, and state-of-the-art machining tools, the facility excels in handling large components such as industrial compressor rotors and gear casings. Quality management is upheld through precise 3D dimensional control systems, ensuring exact measurements and high-quality outcomes. The facility's capabilities extend to manufacturing heavy-duty impellers up to 1,800 millimeters in diameter. Designed for demanding applications, Howden's compressors are engineered to process high volumes, including coke gas compressors capable of managing up to 400,000 cubic meters per hour, driven by either motor or turbine. With inlet and outlet vane control, their environmental compressors efficiently handle flows between 1,000 and 100,000 cubic meters per hour, ensuring high efficiency across a variety of industrial applications. This facility's tailored machining, assembly, and advanced control systems make it a leader in compressor manufacturing. GE's H-class gas turbines are transforming gas power generation by achieving record-breaking efficiency and versatility. As part of GE's HA technology, these turbines offer the highest efficiency for converting natural gas to electricity, with the 9HA combined cycle power plant at EDF in France setting a global record at 62.22% efficiency. Designed for flexibility, HA turbines can operate on various gas types, including liquid fuels, while responding swiftly to grid demands. This adaptability helps them maintain emissions compliance and supports dynamic energy needs. Key to their performance are advanced materials, cutting-edge cooling, aerodynamics, and combustion technologies, which maximize output and reduce water and fuel use. GE's HA technology also emphasizes sustainability, enabling the lowest air emissions in fossil fuel-based power generation. At GE's Test Stand 7, each HA model undergoes rigorous testing, ensuring reliability before deployment. The HA technology has already powered plants worldwide, from France to Japan, the US, and Pakistan, symbolizing GE's dedication to efficient, sustainable energy solutions. These turbines continue to set new standards, reinforcing GE's commitment to delivering reliable power globally. In August, Siemens Energy's service center in Mulheim, Germany, received an urgent repair project for a 100-megawatt steam turbine rotor from Israel. The rotor, along with other critical turbine components, arrived on an Antonov An-124 aircraft, underscoring the project's significance and the time-sensitive nature of the work. The turbine had suffered extensive damage due to an operational error that led to incorrect cooling water flow to a 450 degrees Celsius rotor, causing severe thermal shock. This led to a 0.5 mm warp and a circumferential crack in the rotor's hot inlet area. With the machine offline, each day represented considerable financial loss for the customer, necessitating immediate and efficient action. Once the rotor reached Mulheim, Siemens Energy's specialized service team began by performing a thorough diagnostic assessment. They used advanced 3D scanning technology to create precise models of the rotor, as the original design data was unavailable. This data allowed engineers to accurately map the damage and prepare for complex repairs. Fault analysis revealed the need for heat treatment to correct the rotor's distortion, a procedure requiring vertical positioning. Custom fixtures and lifting equipment were constructed to reorient the rotor, allowing controlled heat treatment which lasted approximately a week. Simultaneously, the workshop identified additional issues, including damage to the first row of turbine blades due to the initial stress. These blades were removed, measured, and replaced with newly manufactured ones. Realigning the rotor's centerline required meticulous machining and laser deposition welding to restore the correct dimensions in the bearing areas. This precise work minimized heat impact on the material, preserving structural integrity. The final phase involved high-speed balancing, a crucial step to ensure the rotor's stability at operational speeds. The Mulheim facility's advanced balancing bunker can handle rotors up to 32 tons and 12,500 revolutions per minute, providing precise quality control. After 3 months, the fully restored rotor was returned to the customer. The steam turbine repair industry plays a vital role in power generation, ensuring the efficiency and reliability of equipment crucial to energy production. With many steam turbines operating continuously, regular maintenance and repair are essential to prevent forced outages and to optimize performance. Turbine Generator Maintenance (TGM) has established itself as a leader in this field, offering a range of comprehensive services that include inspections, repairs, and efficiency improvements. The workshop's turnkey inspections are comprehensive service packages that include all necessary elements to complete a full turbine overhaul. These inspections are designed to identify potential issues before they escalate, which minimizes the risk of unplanned outages. The workshop provides all aspects of inspection, from technical direction and project management to parts sourcing, tooling, and on-site labor. This approach ensures a streamlined process with overseeing each phase of the repair cycle. The goal of turnkey inspections is to reduce downtime and improve the efficiency of the turbine. According to industry data, the average outage for steam turbine repairs can range from 2 to 6 weeks, depending on the scope of work required. The inspection process goes beyond standard open clean close procedures. The inspections are tailored to the specific needs of each client, as detailed in the statement of work. So, each inspection includes in-depth measurements of critical turbine components and clearances at multiple locations, capturing extensive data that serves as a benchmark for future inspections. The value of such meticulous inspection is significant, as early identification of wear patterns and component degradation can prevent catastrophic failures. When deviations from specifications or potential damages are detected, the workshop conducts a full root cause analysis to understand the underlying issues. This proactive assessment can lead to recommendations for operational changes or maintenance adjustments that prevent recurrence, ultimately aiming to eliminate forced outages. In a recent industry report, it was estimated that forced outages due to turbine failure can cost power plants between $300,000 and $500,000 per day. By taking preventive actions based on their detailed assessments, the workshop helps clients mitigate these costs and extend the operational life of their equipment. The global steam turbine services market is substantial, with a valuation projected to surpass $32 billion by 2026, growing at a compound annual growth rate (CAGR) of 5.2% from 2021. As of 2022, over 30,000 steam turbines are in active use globally, with many nearing or exceeding 30 years of operation. Aging equipment, combined with stricter regulatory standards, drives demand for frequent inspections, repairs, and overhauls. The United States, China, India, and Europe account for a significant portion of this market, given their substantial installed base of steam-powered energy facilities. Repair services for steam turbines vary widely, from minor in situ repairs to extensive refurbishments that require specialized equipment and facilities. Key repair areas include blade replacement and repair, turbine blades typically made from high-performance alloys, face wear from high-speed rotation and exposure to steam. Repair or replacement can restore efficiency. A complete blade replacement may cost from $20,000 to $100,000, depending on the blade type and material. Rotor refurbishment. Rotors, the rotating shafts of turbines, can experience fatigue and stress over time. Refurbishing a rotor involves remachining, stress relieving, and balancing, which typically costs between $200,000 and $500,000. Seal and bearing replacement. Proper seals and bearings are critical for minimizing leakage and maintaining performance. Replacing seals and bearings can cost between $10,000 and $50,000. Control system upgrades. Modernizing turbine control systems can improve efficiency and reliability. Upgrades often include installing new sensors, software, and hardware, costing $50,000 to $250,000. Advanced repair techniques, such as laser cladding, additive manufacturing, and non-destructive testing (NDT), have become increasingly important in the industry. Laser cladding. This process involves melting material onto worn turbine parts, restoring surfaces without the need for replacement. This can save up to 60% of the replacement cost for specific parts. Non-destructive testing (NDT). Ultrasound and radiographic techniques help detect cracks and other defects early, reducing the risk of severe breakdowns. NDT services typically cost between $5,000 and $15,000 per turbine, depending on the testing scope. Repairing steam turbines presents unique challenges. First, downtime for repairs can be costly, with power plants incurring losses of up to $50,000 per day. As a result, rapid, high-quality repair services are necessary to minimize shutdown time. Furthermore, there is a global shortage of skilled engineers and technicians trained in steam turbine repair, especially in developing regions. The steam turbine repair industry is expected to grow as power plants extend the lifespans of their equipment and adopt more environmentally friendly practices. Additionally, with more companies looking to achieve net zero emissions, there is an increased demand for retrofitting turbines to operate with lower emissions and greater efficiency. The use of digital tools, like predictive maintenance powered by machine learning, could reduce unplanned downtime by up to 30%. Highlighting a promising direction for the industry. The armature rewind process begins by removing the old windings from the armature and fitting it with a brand new commutator. Before proceeding, technicians perform high-voltage pressure and bar-to-bar tests to confirm the integrity of the armature. Insulation is then meticulously inserted to prepare the slots for coil insertion, ensuring a firm and reliable foundation. High-trax coils, designed for optimal performance, are inserted with precision, and the coil ends are carefully positioned into the commutator slots. A slotted wedge is used to secure the coils in place, setting the stage for TIG tungsten inert gas welding, which fuses components with strong, clean welds that enhance durability. Following the welding stage, the epoxy vacuum pressure impregnation (VPI) process is initiated. The armature is lowered into the VPI tank, where pressures are calibrated for optimal resin penetration. The resin is introduced into the impregnation vessel, completely enveloping the armature coils to insulate and protect against electrical and mechanical stresses. Once the VPI process is complete, the armature is removed from the tank and a durable banding is applied to ensure structural stability. A dial indicator then verifies that the armature is running true, reducing vibration risks. The commutator undergoes a series of skimming and undercutting steps to ensure smooth electrical contacts. Initially, the commutator is skimmed to prepare the surface, and automated machines, guided by lasers for precision, undercut the commutator to achieve optimal slot depth and consistency. A touchscreen controller with a magnified view allows for high-precision adjustments, further refining the cutting accuracy. A final skim of the commutator with diamond-tip tooling smooths the surface, while debris is meticulously cleaned from between segments. To conclude the rewind process, technicians conduct mechanical checks, data logging, and balancing. The armature is rotated to analyze balance, and weights are added to meet specified balance tolerances. This detailed, methodical process results in a high-trax rewound armature that delivers reliable performance in demanding traction motor applications. The production process of specialist high-voltage HV coils at Turnkey combines advanced technology, precision engineering, and stringent quality control to ensure reliability in demanding industrial applications. The workshops, equipped with automated winding and taping machines, produce windings for both new machines and repair projects, covering low, medium, and high-voltage coils. Each coil is meticulously crafted in Germany, with HV Coil Division focusing on delivering high-quality, durable products, particularly suited to complex applications in the energy and heavy machinery sectors. The workshop provides both new coil designs and reverse engineering services, enhanced through CAD technology for insulation optimization. Every design is thoroughly analyzed for electromagnetic, mechanical, and thermal performance, following ISO standards. The insulation systems use premium materials, sourced from leading suppliers like Von Roll and Isovolta, to meet high-endurance requirements. Insulation options include resin-rich and vacuum pressure impregnation (VPI) systems, with options up to thermal class C for high-temperature environments. Corona discharge protection is provided by conductive tapes that shield against stress and degradation. The winding workshop is automated, delivering high accuracy and consistency. The automated shaping and taping machines maintain precision, while electronically controlled tensioning ensures uniform layering. This process is closely monitored, and all manufacturing data is securely stored, facilitating accurate reproduction of each coil design. The workshop employs resin-rich and VPI technologies for insulation, including the H-Seal multi-stage pressing process, which optimizes resin flow and reduces mechanical stress, yielding rigid coils with uniform cross-sections and excellent durability. The quality assurance protocols exceed industry norms, utilizing Baker SKF and Omicron equipment for extensive testing at every production stage. High-voltage surge and high-pot tests validate insulation integrity, while TAN, delta, tip-up, and partial discharge (PD) tests detect any voids, moisture, or contaminants, ensuring the longevity and reliability of each coil. The rigorous testing regimen simulates operational conditions, confirming each coil's capacity to handle industrial drive demands.